Okay, so as we look at this, I really don't want to take too long with this problem, but as we, can look at the situation, just quick answers on this. What kind of distribution are we looking at when we look at part C?
Binomial.
It's binomial. There you go. So we're looking, and how do we know it's binomial?
We have a set number of trials and a set number of successes.
There you go. That's really what we're looking for. So we got 10 trials, 2 successes. Now, the only other question I'm going to ask is you would calculate this on your calculator. You wouldn't do this by hand. All right. And would you use binomial CDF or PDF for this problem?
PDF.
That would indeed be PDF. So just to wrap it up real quick, PDF is used when we're looking for the probability of exactly X number of successes out of N. CDF is when it's cumulative up to X number of successes. So if we had done CDF, we would have found the probability of 0, 1, and 2 successes. And we don't want that. All right. So that's really all I wanted to discuss there. There could be more to it. I didn't talk about every part. So if you did have questions on that, you can stick around after class. We can talk about it. Now I wanted to move to this one, I believe. Okay, and in this case, it's a challenging problem. I think just to wrap your head around it and make sure you're doing exactly what they're asking. But I'm just gonna go through it, so I'm not asking you guys for input on this one. But hopefully what you realize is that we are looking at a sampling distribution of differences between samples. And because we know the population, we know where the population values are right here, up in the top few sentences. Okay, now the last sentences are all about the different samples that we have. But because we know the population, we know that this sampling distribution is going to center at population proportion 1 minus population proportion, well, I'll say D and E. That's where the mean is going to be. And we can come up with the standard deviation of this. And that's what we're looking for in this problem. Now, even though it says p hat for everything, we're really using the population values for the most part to come up with this. So let's kind of see what that means. When we're trying to find the mean of this distribution, now I know it's proportions, but we still have the mean of the distribution. The mean of p hat sub D minus p hat sub E is going to be the mean of p hat sub D minus the mean of p hat sub E. And we already know what the mean of these are. Those are these population values up at the top. Now, once we got out of this unit, we never knew the population values anymore. So that's why your headspace might be where you're thinking, oh, well, I'm using the p hat for all this stuff. But in this unit alone, we have the population values, so we can just use those. Anyway, so the population mean for D is going to be 0.3. That's that 30% right here. This is the mean of p hat sub D. And so the 20% right here is going to be the mean of p hat sub E. So it's going to be 0.3 minus 0.2, which is 0.1. So the mean of this will be 0.1. The standard deviation, we will need to do our other calculation, which is going to be, I might just erase this so I have some room to write. The standard deviation of a difference of proportions sampling distribution is, and this is where I was saying it required using some formulas that we already know, but at this point in our review, technically we wouldn't have known them yet, but you already know them anyway. So that's going to be P sub D times 1 minus P sub D. This is the population proportion, not the sample one, over N of D. Now, this is where we would have to use a sample value because we're trying to figure out what is the standard deviation, what is the variance rather, of this particular sampling distribution for this sample size. All right, so P sub E times 1 minus P sub E over N sub E. So now we could go through and do the calculations. I really don't want to plug all those values in, but the same values right here, it'd be 0.3 would go in for P sub D, 0.2 would go in right here. And these values would come from the sample. So when we were looking at D, we had 40. So 40 would go in right here, and 60 was our other sample. So that would go in right here. Anyways, once we found the variances of those, added them together and square rooted to get the standard deviation, of I think it's 0.089 essentially. So hopefully those of you who did this problem were able to get the same answers. And now part C, can it be assumed that this is approximately normal? This is where we would be checking our conditions. So we want to check to make sure it's random. And it does say random sample, so we're good there. Is it 10%? I think it's fair to say that 40 and 60 is less than 10% of all turtles. Let's hope so. And finally, the large counts. And when we have populations, we can check each count separately. Sometimes we do pooled counts, but that's typically whenever we are doing the 2 sample Z test. We would find a pooled sample to determine if that large counts condition is met. So this would be N times P, and N times 1 minus P is met greater than or equal to 10. All right, all that fun stuff. I'm not going to run through it except to say that's what we would be checking. Okay, I would do that for each of my sample sizes. All right, now the last thing, I'm going to stop. Well, yeah, I need to stop sharing for a second and then bring up a new share, which is this one, I believe. Dang it, no. I chose poorly. There we go. Now we're ready to go through this. This one was somewhat complicated. The first two, I would argue, are not complicated. I hope the first two are not complicated because we're just finding, well, in this one, it's a basic probability problem. So you could do that. But the second one, expected value, you can find it by creating list 1 and list 2 on your calculator. You could also just do 3 times 0.15. So it's these two multiplied together plus these two multiplied together and so on. So ... plus 7, dang it, what am I doing? 7 times 0.05. So once you do that, you can get your expected value. But your calculator does it very quickly. So that's the first part. And what you'd get here is an expected value. I'm going to call this X. Well, it calls it X anyway. This is 4.55. So that is not the tricky part of this problem. Is right here. So this, all those possible outcomes and then the expected value that we came up with, that was all counting on him shooting short. So apparently there's this lake in the middle of the shot, and all those expected values are assuming that he does a short shot to start off with, and then he goes from there. But there is another possibility. This is where we add a wrinkle. It says he could attempt a long shot to go over the lake. If he makes it, his expected value improves to 4.2. But if he doesn't make it and it lands in the lake, then it increases to 5.4. So we could go from 4.55. If he makes it, and I'll put a 0.4 right here to say it's 40% chance, he's 4.2. If he misses, which means it's a 0.6 chance of that, it's a 5.4. Okay, so the question that we're now going to answer is, suppose the probability is 0.4. So that's where it's actually introduced. I kind of jumped ahead a little bit. If the probability is 0.4, and that's what I wrote here, which approach is better in terms of improving the expected value of the score? And I'm just going to run through it quickly, but this one might be one where you need to sit there and think about it for a while. And the approach here is that we know that he's going for this shot. He's either going to make it or it's going to fall in the lake. They're not giving us this opportunity that like, oh, he's going for the long shot, but he lands on the near side. So we're assuming he either makes it in the lake or makes it over the lake. So there are only two outcomes. He either ends with an expected value of 4.2 or an expected value of 5.4. And he's got a 40% chance of getting this expected value, and a 60% chance of this expected value. So that's kind of the conceptual difficulty with all this, is figuring out what to do. But once we know that these are the outcomes, I'll just put X right here. This is the probability of these outcomes. And we got a probability distribution. I can just create list 1 and list 2. And actually in this case, just for the sake of the next problem, it might be good to see it this way. 4.2 times 0.4 plus 5.4 times 0.6 equals, and then, well, we'll find out what that equals. It is, I can't quite remember. I think it's 4.92. I did the math earlier. So when you get this, it's 4.92. And if I'm off, I'm only off by a little. I guess I could plug that in the calculator. But we started with an expected value of 4.55. And then when Miguel tried the long shot, it increased his expected value to 4.92. So it is not, we can conclude that it's not a good idea for him to try the long shot, because it's actually going to be worse for him in the long run. Okay, so if you're with me on that, I'm going to clear everything. And we just answered part C. And now we get to the last one. 4.55 is the original expected value. 4.92 is what we came up with. Actually, we don't need the 4.92 for this last problem, but we want to figure out, okay, so at a 40% chance, it's no good. So what probability would be required for the long hit to be the better choice? So we already set up the equation once, 4.2, but instead of using 40% as my probability, I'm just going to use P. What's the probability of making it? And I know that this is my probability of making it because 4.2 is the better outcome. Plus 5.4 times 1 minus P. And that has to, now we don't know, we're not just solving for it. We're going to set this equal to 4.55. And the reason is we want this outcome right here to be at least as good as this outcome that we started with, the original expected value. So what value of P will get us that? And I'm not actually going to do all the algebra. You could, it's pretty much a basic algebra problem at this point, but eventually you'd find that the probability is 0.708. So you'd have to have over a 70% probability of making it across the lake before you'd even want to attempt it. Otherwise, you're better off shooting it short, and yeah, that's basically it. A little bit complicated, certainly wrapping your head around that one, but not too bad on the calculations front. All right, so now I'm going to go back to our presentation. find it. There it is. Okay. Took me a second, but we're ready to go. Now let's kind of get started with our Unit 8 review. We're going to look through 9 problems total. And there are some other ones I'm not going to go through, but if you need to go through some more before you leave today, we can look at some other problems. Unit 8 was dealing with confidence intervals. This is the very first inference test we introduced. And we're only looking at one sample proportion or one sample mean. We had a general formula that looked like this. We have our specific formulas on the right, if it was based on means or proportions. And this is where the 4-step process was introduced, the state, plan, do, and conclude. I want to clarify, you do not have to follow it exactly, though it is a very nice way of keeping it straight and to make sure that you have everything that you need in your answer. So that's why we kind of kept it with the same format over and over again. We had to interpret confidence levels and confidence intervals. Those are 2 different things. We'll see some problems related to that. All right, well, let's just jump into it. We've got a national survey. We have a 90% confidence interval. And we've got, basically the question is, what's the correct interpretation of this interval? So it's how many hours adult workers work per week. 90% confidence interval was 41.18 to 42.63. Let's now see. We are, so just before I look at the answer choices and pick what I think is right, there's different ways we could describe this, but one way is if we had repeated samples from the population, 90% of our confidence intervals, well, actually, I'm kind of describing confidence level with that one. So let's just focus on this interval. We'll come back to what I was talking about in a minute. 90% confidence interval says that we are 90% confident that the true mean, the true population, mean, will fall somewhere between 41.18 and 42.63. And it's important that we're talking about the population mean is going to fall in that range, because we already know where the sample mean is. It's right in the middle of our confidence interval. So we are 90% confident. So I will go ahead and cross out anything that doesn't show that. So between these two, we could say 90% confident that hours worked per week for employed adults in the sample. Okay, and like we just said, it's not for the samples, for the population. So I just want to cross that one out. We are 90% confident that the number of hours worked per week for all employed adults is between 41.18 and 42.63 hours. So this is for all employed adults. We're talking about the population. This is our interpretation here. Okay. Another thing that came up, if we look at our basic formula, is plus or minus. Really, we could say the margin of error. And our margin of error is the critical value times the standard error. So we can use this when we're dealing with proportions only. It's important that we're dealing with proportions, because with means, we can't do these kinds of calculations. But if I wanted a margin of error of no more than 3%, that's 0.03. And I can substitute. In fact, real quick, I want to do this. It's going to be p hat, or I'm sorry. Margin of error is going to equal a critical value, which is going to be a z star value, times, this is going to be the square root of p hat times 1 minus p hat all over n. So if I start trying to fill this in, I already put the 0.03 for my margin of error. N is, what we're solving for, obviously. And p hat, we don't know. So if we don't know it, the most conservative estimate we can do is to use 0.5. So anyways, we've got 0.5 going on, and I'm not going to finish it from there. But remember, which is closest to the minimum number? I actually didn't do the calculation to figure out what the answer is, but none of those are likely to be exactly accurate. So you want to find the minimum. So if we got a number here, I guess we could do the math real quick, but if I got some answer here, so n equals something, it is probably going to have a decimal. Let's say it ends in a 0.7. I would need to make sure I rounded up. So this could have actually been 0.01, right? And I'd still round up to the next person. So if you have a number that's really close, but it's just under, then you need to round up to find the closest one that's above n. Okay, I don't want to say any more about that, but if you have questions, you can come back to it. So this is a question where they're asking us to interpret a confidence level. And now this is what I was talking about earlier, where with confidence levels, the interpretation is that if we repeatedly sampled, we would expect 95%, or we're confident that 95% of our confidence intervals would capture the true mean, the true population mean. So I like this way that it started off. If we repeatedly sampled this field, taking samples of 80 plants and constructing 95% confidence intervals, then, and so I like that beginning, so I'm going to cross these two off because those do something different. Approximately 95% of these intervals would include the population mean number of alfalfa weevils on an alfalfa plant in this field. That one actually looks good. So let's see what's wrong with the other two. So the what do you call that? The dependent clause is the same for all of these. So let's see what's going on here. Approximately 95% of these intervals would include the sample mean. No, all of them would include the sample mean. So that's not right. Then 95% of these intervals would include 2.5. Well, no, that wouldn't happen either. Because 2.5 is just a sample mean. We're looking for the population, and we would expect the population mean to be captured 95% of the time, not a specific sample mean. So there you go. All right, this is the last one we're going to look at for Unit 8. We've got a random sample. They basically want us to find the confidence interval. So to do this, we first of all need to establish, is this means or proportions? And it doesn't straight up say, well, it does say proportion right there. But even if it didn't, we can see there's 300 students and 180 said they do. So it counts, and we could get a proportion. So p hat in this case is going to be 180 out of 300. That's 0.6. The sample size is 300. And we are using Z star. And I believe that's all we need here. I don't know what Z star is for 98%, so we'll look that up later. But I know that it's going to be stat plus or minus the critical value times the standard error. So that's going to be p hat plus or minus Z star times the square root of p hat times 1 minus p hat all over n. And now I can plug in, I'm going to have 0.6 plus or minus. I'll leave Z star blank for right now. P hat is 0.6. This is 1 minus 0.6. I guess I don't need the 1 minus. I'm just going to get rid of that. It's going to be 0.4. And then over n, which is 300. Now, I can't solve this until I get the critical value. Because it's a Z star, it's going to be the bottom row of table B. So you got table B with all these values. All right, if we go down to the very bottom row, this is where the degrees of freedom is infinity. And these, I would just find where my 98% confidence level is. And I would just find that value on the very bottom row. I will do that off screen real quick, but you guys can look that up on your own. If I can find where I put that. All right, so I got When I look at the bottom row for 98%, it's 2.326. .326, and I will not finish doing the calculation from here, but you can find out what the correct interval is for that. Okay, good times. All right. I'm going to skip over these problems. If you want to look at those later and you have questions, certainly you can do so. But Unit 9 is all about hypothesis testing. And we're still looking at just one sample mean or one sample proportion. Unit 10 is where we do the two sample. Hypotheses, this is where we introduced it, null and alternative. And general formula, we have that given right here. The specific formulas are on the right. The test statistic is essentially a z-score telling you how out of the ordinary, I should put the, okay, well, no, the statistic is fine. I don't need to cross that out. This is basically a z-score telling you how out of the ordinary your sample statistic was for the sampling distribution. So if you get a sample mean that's really, really far from what the null hypothesis is, then that would tell you it's probably statistically significant. And likewise for sample proportions. So this is essentially a z-score. And if you can remember that, that's going to make all this concept fall into place a lot better. Interpretation, p-value. So you need to be able to interpret a p-value and kind of state whether you're going to reject or fail to reject the null hypothesis. And the last thing is type 1 and type 2 error and power. This may be something you've forgotten, but I want to remind you of the boy who cried wolf. That's maybe a mnemonic that can help keep that straight. We will talk about all of these concepts with some of the problems here. So I'll just jump into it. The first one is asking us to interpret the conclusion, which in essence is asking us to interpret a p-value. Not exactly. There could be a different way of interpreting a p-value, which is the probability of getting the test statistic that you got or more extreme, assuming the null hypothesis is true. This is asking us to interpret the conclusion. So if our significance level is 0.05 and the p-value is 0.08, we fail to reject the null hypothesis. And without even looking at the answers, the template that we would say is because our p-value is higher than the significance level, we fail to reject the null hypothesis. There is convincing evidence, there is not convincing evidence that the machine is dispensing, right here's the alternative hypothesis, that the machine is dispensing less than 12 ounces. Okay, now we didn't really talk about the context, but it'll make sense in the end. Okay, so because the p-value is greater than the significance level, that's good. I like this as a start. That might not be my answer, but I'm going to cross out everything that doesn't start that way. The p-value is not less than the significance level. So I only have two choices. There is convincing evidence that the population mean number of ounces dispensed into a bottle is 12 ounces. Well, wait, there's another one right here because I was like, I don't like either of those answers. I shouldn't have crossed that one out. Because the p-value is greater than the significance level, there is convincing evidence that the population mean number of ounces dispensed into a bottle is less than 12 ounces. Now remember, our conclusion is that there's not convincing evidence. So let's see what the last one says. Because the p-value is greater than the significance level, there's not convincing evidence that the population mean number of ounces dispensed into a bottle is less than 12. We're really just making a decision on rejecting or failing to reject the null hypothesis. We're not saying the null hypothesis is true. We're saying that we can't reject it. So there's our answer. Okay. So we've got a question here about, we're about to run a test, and how would we increase the power of our test? and this is maybe where I need to spend a little bit of time reminding you that we have a null hypothesis that the true population proportion is somewhere. But there is a true population that the distribution might not be right there. Let's pretend that our population is really right here. And we never know this, okay? So this is a conceptual thing to understand, but we'll never know where the true population distribution is. But just conceptually here, if we could imagine that the population lived over there, then all of our samples have to come from the population. And there's a true population mean. So anyways, we have a significance level. And I'm going to put it right there. So this little wedge right here represents our significance level. It's also the region that determines our type 1 error. So I'm going to put type 1 right here. So it's alpha, and I'm going to put equals type 1 error. All right, because that type 1 is whenever we reject the null and we should not have. And so there's a 5, if this is a 0.05 level, then there's a 5% chance of that happening. But where this exists, where that significance level is, this critical value, we can create a line right here. In the population, when we're drawing from the population, there are two outcomes, assuming that the null is not true. There are two outcomes. We could, let me get a different color. We could end up in this region right here. We get a sample where the sample mean ends up over here. And we failed to reject the null hypothesis when we should have. This is type 2 error. So we don't reject the null hypothesis even though we should have. And then we could end up in this region right here, which is we reject the null hypothesis and we should have. And this is the power of the test. Okay. So knowing that, there are 3 ways of increasing the power of your test, and that's what this question is all about. If we raise the sample size, these distributions, like we are hopefully well aware of by now, would go from, a distribution like that to something more like this. And there's less overlap at that point. So by increasing the sample size, that would be a good thing to do. We could increase the significance level, because what that would do is it would push this line right here further to the left. And by doing that, the power region will get bigger. All right, so alpha level could go up. The other thing we could do is make these two distributions further apart. So if I could push this population over somehow, then the effect size, so I'm just going to put ES for effect size. If the effect size was bigger, then it'd be easier to reject the null hypothesis. Okay. Anything that helps us reject the null hypothesis will increase the power of the test. So now that we've done that, we will kind of look at our answers. So we want the biggest sample size we can find. So the biggest sample size is right here, these two. And between these two, we want the biggest alpha, but that doesn't seem to be an option. So I'm just going to cross that one out. So now the only other thing we can look at is the biggest effect size. So the biggest effect size, if the true proportion, or if the hypothesized proportion, so this is H sub naught right here, a null hypothesis. If the null is 20, then the effect size would need to be far away from that. And right here, 50% is further away. So this would be our best answer. Okay, a lot of concepts thrown into that, but hopefully it was all coming back. And just remember your type 1, type 2 error. In The Boy Who Cried Wolf, the villagers rejected the null when they should not have, and that was a type 1 error. And then later they failed to reject the null hypothesis when they should have. And that was their type 2 error. And the null here is that there is no wolf. Okay, so this question is all about, is it appropriate to perform a hypothesis test? Have we met our conditions? Is it random? Is it 10%? And have we met normality condition? We can just say, is it normal? So we first of all need to determine, are we looking at proportions or means? And it looks like this is means. So we have, in this case, the central limit theorem is what we're turning to for normality. Is it random? Well, there's a random sample right here, so we're good. 10%. Well, our sample size is 18, so that is less than 10% of the population. We're talking about insurance, and there it says right here, thousands of customers. So we're good on that. Now the other question is it approximately normal? And for the central limit to be met, our sample size has to be greater than or equal to 30. And we can see, no, we did not meet that. Now we could still be okay if the population is approximately normal. All right, so now we need to kind of see what's going on. So if I look at this, it says basically the distribution is describing the first sentence. Actually, in the second sentence, it says they know that most customers have 0 payouts, and a few have substantial payouts. So our distribution probably looks something like this. So the population is not approximately normally distributed. So we can find an answer that says we failed to meet this condition, it's not appropriate. I'm not going to read through it, but you guys could come back to this and figure out which is the best one to answer for that. All right. Now we've got a hypothesis test where we need to figure out, first of all, is it proportions or means? I see the word proportion. Honestly, I'm just scanning and looking for one of those words. And I see proportion, so that's good. So the sample statistic here is going to be, well, first of all, stat minus parameter over the standard error, and it will be my test statistic. I know it's going to be a z statistic, but anyways, in this case, it's going to be p hat minus p divided by the standard error. Now that's what I would be doing in order to figure this out. But if I look at this problem, it never tells me what my p hat is. So it does tell me this 0.2, but if I read this carefully, we're testing against that. So that's my null hypothesis, which means that's my p. So I mean, the only thing I can plug in right here is minus 0.2, and then I don't know anything about the standard error. Remember, that's p hat times 1 minus p hat all over n. Or, sorry, it's p. No. Now I'm forgetting. Yeah, we use p for this. That seems, yes. I had to think through that. But anyways, bottom line for this particular problem, it's 2.25. Because it tells us right here, the test statistic is 2.25. So knowing that it's a z statistic, all I need to know is that if I can think straight. All I need to know is that I'm doing a normal CDF calculation. I'm going to go from 2.25 to positive infinity with a standardized normal model, and I can get my answer. If I needed to calculate the test statistic, that's normal CDF, I should say. Anyways, we can go from there. All right, pretty straightforward when they give you the test statistic. All right, and the last one that we're going to look through, it's basically asking how would a type 1 error occur in the situation? This is when we reject null So we're rejecting the null incorrectly. Okay. So we are looking at machines at a bottling plant filling to 12 ounces. We've already seen a scenario. The quality control officer wants to make sure that the bottles are being filled to the appropriate amount. The null hypothesis is that the mean is at least 12. So the alternative is that the mean is less than 12. So if we reject the null, and we should not, then if we read through here, the test does not provide convincing evidence that the mean is less than 12 ounces, but the actual mean is at least 12 ounces. So we want to figure out where it's going to tell us that we rejected the null. So that means we have convincing evidence that the mean is less than 12. There we go. But the actual mean is at least 12. So here we go. The null is true, but we rejected it. So I believe this is our best answer. All right. So very quick overview with all those concepts. There's a few more questions here that I'm not going to go through. Your FRQs tonight. For the Unit 9, I only want you to do A, B, and C. You can certainly try D, E, and I don't know if there's an F, but D and E if you want. But I'm only going to expect you to do A through C. So if you have questions, you can stick around. Otherwise, you can have yourself a wonderful weekend, and I'll see you on Monday.